Hello everyone, I'm Zhaoyang. Due to visa issues, I will make a presentation through this video. The topic of this research is Autonomous Network Configuration Updates, and the title is NetKeeper, Enhancing Network Resilience with Autonomous Network Configuration Update on Traffic Patterns and Anomalies. The presentation is divided into 5 parts. Background, challenges, NetKeeper, evaluation, and conclusion. Modern enterprise networks are becoming increasingly complex and experience frequent changes. Operations and maintenance personnel need to carry out intensive manual intervention for event analysis and configuration management, which leads to errors and inefficiency. Mainstream configuration tools rely on static models and domain-specific languages, which have a high technical barrier and lack intelligent awareness and adaptive handling of abnormal logs and real-time traffic, making it difficult to respond efficiently to dynamic environments. Against this backdrop, traditional static compliance configuration can no longer meet the policies. Intent-based adaptive updates in dynamic scenarios have become the key to achieving high performance and high resilience in networks. To address these challenges, we urgently need to focus on 3 key areas. First, achieving efficient multimodal intent integration to seamlessly translate operational intents and abnormal logs from multiple sources. Second, enhancing resilience through traffic-driven approaches that coordinate configuration decisions with real-time traffic, thereby improving overall network performance. And third, implementing dynamic adaptive automation to enable continuous, automatic, and flexible configuration updates, which will significantly reduce the need for manual intervention. Together, these efforts will pave the way toward a new era of autonomous and intelligent network management. Hence, we introduce NetKeeper, an end-to-end network configuration update framework that translates network intents into corresponding configuration based on the current network state. The system consists of 2 main phases: intent translation and configuration update. First, user intents and abnormal logs are unified and translated into domain-specific language instructions using a large language model. An interpreter verifies the translation, and user feedback ensures its accuracy. Based on the domain-specific language, appropriate APIs are selected for execution to update the network. Simple configurations can be rapidly deployed via directly the API calls, while for global or complex teams, the system invokes a multi-agent reinforcement learning model to intelligently optimize the overall network configuration. This closed-loop process balances efficient response with global optimality. In the multi-agent update phase, each agent focuses on a different type of parameter, such as protocol configurations or link attributes, and collaboratively optimizes the global network state through coordinated decision-making. Each agent adjusts its actions based on real-time feedback, continuously improving policy consistency, traffic load balancing, and overall network performance. This enables intelligent configuration optimization in complex scenarios. Next, we will introduce details of the system. In the intent translation stage, we construct a unified intent model for both natural language intents and network anomaly logs, covering devices, protocols, rules, and more to standardize the network intent space. Since all intents cannot be directly verified for validity, such as whether a specified device exists, we introduce a domain-specific language as an intermediate layer, along with an interpreter that performs both syntactic and logical validation to ensure that the configurations are accurate and executable. After receiving the network intent input, the fine-tuned large language model first parses high-level intents into structured DSL commands. The DSL interpreter then checks these commands for syntax and logic, automatically provides feedback on errors, and supports user corrections. Through the launching framework, validated domain-specific language instructions are passed to backend APIs to carry out the corresponding network update operations. In the network configuration update phase, we focus on three main objectives: higher policy consistency, lower load measurement, and reduced traffic shift. Among these, policy consistency is the primary objective to ensure correct business operations, while the other two metrics are aimed at enhancing network resilience and improving overall network performance. To achieve higher policy consistency, lower congestion, and reduce the network shift in dynamic networks, we need a machinist that can guide network configuration to adapt to diverse attributes and ever-changing traffic patterns. Traditional approaches struggle to comprehensively consider network link properties, traffic dynamics, and changes in the forwarding plan, making it difficult to cope with complex and volatile network environments. In construct, deep reinforcement learning can continuously optimize configuration policies by integrating real-time network states and historical feedback. This enables the system to dynamically adjust routing protocol parameters and link settings, achieving both performance improvement and network stability, and adaptively satisfying network policies and business requirements. At the same time, network configuration updates involve three mutually distinct types of parameters: BGP, OSPF protocol parameters, and link attributes. Relying on a single agent makes it difficult to efficiently handle the large solution space and complex parameter dependencies. Therefore, we adopt a multi-agent collaborative approach. Each agent specializes in updating a specific type of parameter, which not only simplifies the optimization process, but also allows each agent to leverage this domain expertise. Through collaboration and coordination among agents, the system effectively maintains consistency in configuration updates and optimizes overall network performance. Next, we define the state, action, and reward functions for the agents. The network state is constructed based on the current network slice. Using graph embedding techniques, the connectivity between nodes and the attributes of each node are encoded together to form the overall network state. Each agent generates corresponding actions based on its assigned responsibility and the current network state. All actions works collaboratively to update the overall network state. We define two types of reward functions: policy satisfaction reward and network performance reward. Since policy satisfaction is the primary objective, we also introduce dynamic reward mechanisms. First, accumulated penalties for agents that get stuck in local optima. Second, rewards for satisfying new policies and penalties for violating previous policies. In addition, before generating ejections, agents can observe two types of environmental feedback: the specific policy satisfaction status and the utilization rate of each network link. To train the agents above, we use the actor-critic architecture. The model adopts a decentralized actor and a centralized critic architecture. Each agent makes decisions independently and adjusts different parameters based on the globally encoded network state shared via a graph neural network. The critic evaluates the global Q values for the actions taken by all agents, guiding the training process to optimize overall network performance. This design balances efficient local decision-making with global collaborative optimization. The counterfactual multi-agent algorithm is used to train the actor-critic networks. The experimental setup consists of four parts. The datasets include an intent translation dataset and a network topology dataset. The training environment for the agents is a Python-based simulated network environment. For intent translation, we use a fine-tuned ChatGM 6 billion model. Each agent is built using an 8-layer GCN and an 8-layer transformer encoder. We present experimental results in terms of intent translation accuracy, policy consistency, configuration update time, link utilization, and traffic shift. The performance of our approach is compared against NetComplete, GAT, and NetRun. This table shows the intent translation accuracy of NetKeeper, covering both natural language intents and anomaly logs, with an overall translation accuracy of 96%. With the assistance of feedback and the domain-specific language mechanisms, the translation accuracy is improved by 11%. This table shows the policy consistency of NetKeeper after configuration updates, which refers to the satisfaction rate of configurations with respect to forwarding policies. On average, NetKeeper achieves a policy consistency of 99.6% compared to SMT, GAT, and NetRun. This represents improvement of 1.3%, 10.4%, and 1.2% respectively. Configuration synthesis efficiency is crucial for adapting to network changes. The proposed NetKeeper achieves an average network configuration update time of 4.07 seconds, while the time consumption is comparable to NetRun. NetKeeper delivers higher policy consistency and better optimizes network performance. We compared the link utilization of configurations generated by NetKeeper against default, random, and random configurations under different traffic pattern scenarios. On average, NetKeeper reduced link congestion by 5.3%, with an overall network performance improvement of 5.3% over baseline methods. Figure 8 shows the traffic shift caused by configuration updates with NetKeeper under different network scenarios, with an average shift of 5.9%. This represents an 8.7% reduction compared to Netherlands. Also, we intentionally introduced network events to evaluate NetKeeper's awareness and update capabilities in dynamic networks, include policy additions and removals, traffic changes, and topology modifications. As shown in Figure 9, NetKeeper is able to restore policy consistency within nearly 30 time steps, while simultaneously optimizing network performance during configuration updates. And finally, we deployed NetKeeper in an enterprise network for testing, achieving a configuration update accuracy of 94.8%. It improved network resilience by 39.4% and reduced manual intervention by 51.5%. Finally, I will summarize my work. First, a bidirectional intent translation interface is introduced for automated policy management and anomaly response. Second, a traffic-aware, goal-driven multi-agent update model is designed for autonomous network resilience. The last, NetKeeper is proposed for self-management, consistent, and efficient autonomous network configuration under anomalies, enabling autonomous policy generation and developing fine-grained application-aware traffic profiling are key future directions. Thank you for your listening. If you have any questions, please contact me through my email.